Hello, everyone. My name is Gary Stroick, and we are going to be presenting today some training slides for the Midwest High Power Rocket Competition, which is being conducted in 2025 for the Minnesota Space Grant Consortium. We're going to be presenting information on a variety of topics with this presentation today. And let me just hand it over to James Flaten to introduce himself.
Howdy, I'm James Flaten. I work at the University of Minnesota Twin Cities, and I represent NASA's Minnesota Space Grant Consortium. And as Gary mentioned, this recording is for the teams who are participating in the Space Grant Midwest competition in 2024-2025. On the other hand, we think that these topics would be useful to other people and people in this competition in later years. So Gary made up a bunch of slides. Thank you, Gary. Let me share those slides and we will proceed. So we just call these the high power rocketry training slides. This is not totally inclusive, but basically this will give people a good idea about at least a few topics, including very important topics. So the first section is transition to high power. In this particular case, this means transition from model rocketry to high power rocketry. And so one of the expectations in this competition is that people get some expected model rocketry, but you should be aware that there's much more to do and much more to learn if you're going to then go on to high power rocketry. So, for instance, rocket design. Basically, high power rockets and model rockets look very similar, but there are differences, especially performance differences and also differences associated with how you build them, the kind of materials you use, the sizes. High power, of course, uses more powerful motors. And there are many things to consider. And remember, the switch from model rocketry to high power rocketry is based on the motor classification. H is for high power. So A through G would be model rockets, and then H and beyond would be high power rockets. And then Gary, at any point in any slide, by all means, jump in, but I'm just going to push forward.
All right.
So just some comments about models versus high power. So typically model rockets don't go as high, they don't go as fast, they don't accelerate as quickly, and the atmospheric pressure that they experience does not vary as much, and the temperatures they experience don't vary as much. On the other hand, the high power rockets that we are building, at least for this competition, aren't going to go to 450,000 feet, but it's possible for high power rockets to literally get into outer space. We, on the other hand, will typically be pushing our high power rockets to a few thousand feet, but the speeds can be high, the accelerations can be very high, things can break if you don't build them very carefully. So because the motors are bigger for high power rockets, not unexpectedly, the rockets themselves are bigger. The diameters, rather than being an inch or two, tend to be several inches across. The length, instead of being a foot or two, might be several feet. And the weights, instead of being a few ounces, can be a few pounds for high power rockets. The materials vary as well. So typically a model rocket would be built with cardboard, paper sometimes, balsa wood fins or plastic fins, molded plastic parts. High power rockets, on the other hand, typically would use for airframes canvas phenolic or phenolic, which is kind of souped up cardboard, or fiberglass or carbon fiber. Blue tube is another example of sort of a cardboard type product with impregnated to make it much stronger. And then the nose cones can be plastic, but sometimes they have aluminum parts to them. The fins can be fiberglass or canvas phenolic, but they could also be made of plywood, but not balsa wood in the case of high power rockets. When you're putting things together, you would use typically epoxies, two-part epoxies instead of glue. So a model rocket might be built with wood glue or white glue, or possibly super glue, plastic glue. On the other hand, for high power rockets, you almost always use two-part structural epoxies. JB Weld is an example of one that is particularly useful for high temperature applications. So things that need to be glued together in the vicinity of the motor nozzle, which can get very hot during flight, will need something more serious, possibly JB Weld for its epoxy. And then certain parts of a high power rocket typically could be fastened together, not glued together. So when you're doing fasteners, you would use bolts or nuts, screws, threaded inserts. Threaded rods are very typically used to hold an avionics bay, an av bay together, because during the course of a high power rocket flight, you're going to have ejections and you will take your recovery harness and it will be pulled very tightly. And you have to make sure that every part of the rocket is very strong in tension, and threaded rods is one way to make that specific part of a high power rocket very strong in tension. Generally speaking, this is based on years of experience for people who do rocketry. The majority, in fact, of failures in a given flight typically happen on the way down. It's not too hard to go up, it's hard to come down safely. So in the case of model rockets, your recovery typically would be a parachute, a single parachute, or maybe a streamer, maybe even tumble recovery, if you have a very non-aerodynamic vehicle. You just have to make sure that your parachute doesn't snap off. And so if you glue the shock cord, the glue joints can come apart. If the shock cord is elastic and you extend it too hard, you can break the elastic. Model rockets almost always fly with a motor and a motor eject, so a single ejection charge. High power rockets do many of the same things, but just significantly stronger, okay? So you might have multiple parachutes, like a drogue at apogee and a main chute to open up as you approach the ground. Hardly ever a streamer or tumble recovery in the case of high power rockets. Basically, your shock cords, your retention harnesses tend to be made of Kevlar or nylon, something stronger, hardly ever elastic. And then they are attached to metal parts, forged eye bolts. So avoid eye bolts that are only bent over because they can unbend on you. Forged eye bolts are much better and stronger, or U-bolt attachments. And then the ejection charges, besides the motor eject, typically you would put in your own ejection charges, which could be Pyrodex or black powder, or possibly some sort of a compressed gas like carbon dioxide. Of course, you need to choose the right parachute to make sure you come down at a safe rate as well. What you might carry on board as far as avionics, on a model rocketry, you could carry a camera. There are some model rockets that are sold to carry very small cameras and a data logger, an altimeter 2, for instance, or altimeter 3. In our competition, we in fact require people to carry such a data logger. High power rockets, on the other hand, often carry much more than that as far as avionics. Okay, altimeters, so a real altimeter, which allows for firing ejection charges and bringing out parachutes at different parts in the flight, staging or air starting to get motors started while you're already in the air. And then also souped up data loggers. So call these flight computers for data collection and sometimes for opening and closing air brakes and things like that. When you go high, you're more likely to lose things. And so trackers are recommended pretty much on all flights and required on certain flights. In the case of the Minnesota TripoliMN Club, they require trackers on all certification flights and also on all flights that fly 3,000 feet or higher. I would just describe that as any rocket that's likely to fly out of sight, literally out of sight. Okay, so you could also put on some sort of an audio beacon. I see that's mentioned as a screamer here. That allows you to hear the rocket when you get close to it if you know where to look, but if you don't know where to look, that won't help you very much. And then high power rockets, typically the avionics don't get turned on until the rocket is already buttoned up. So you need some sort of a switch on the outside, screw switches or perhaps magnetic switches, or you might be able to turn on rocket avionics by Wi-Fi. And then the power, basically the power, instead of being button batteries, often would be rechargeable lithium batteries or perhaps alkaline 9-volt batteries for certain kinds of altimeters. So lots more to think about avionics-wise for high power rockets. That's what makes it fun. And then here's just a list. So I already mentioned the fact that model rockets are essentially A or half A or quarter A. That's the smallest. These are all impulse classes up to the letter G. And then that big line there means this is where high power starts. And high power, H and I would be considered level 1 for certification purposes. JKL would be level 2 for certification. But it turns out that high power motors go bigger than that, although they're not always commercially available. If you want to fly really, really big ones, you might have to build the motors yourself. And some people get involved in building motors themselves, even at slightly lower or slightly overlapping with the commercially available. We don't do that in our competition. Basically, we only use commercially available motors, and typically we say in any given year, you must fly an H motor or HI or HIJ, and we rarely go beyond J in our particular competition. Notice that every motor class is actually a factor of 2. So there are low H and there are high H motors, as in there are motors that are very close to the minimum amount of impulse, and then there are motors that literally have about twice as much fuel and are close to the maximum amount, and both of them would be considered H motors. So if you see an H550 motor, for instance, H is the impulse class. I described to my students that's approximately the amount of fuel you have. And then the 550 is the average thrust in newtons. And so 550 is a real kick in the pants motor. I'll turn it over to Gary with some comments about minimum diameter, which is of particular interest to people in the 2024-2025 competition where you're trying to go as high as possible.
All right, so today we're going to talk about those. As James just stated, one of the challenges today is for the 2024-2025 competition is to go as high as possible with an H550 motor. So again, construction materials, we've talked a little bit about that earlier with respect to the model rocket versus high power rockets. But one of the things that we didn't discuss earlier happened to be the motor retainers. And so the motor retainers in a model rocket is usually just spring steel retainer that kind of clips on the side of the motor and holds it in place. That is not strong enough really to hold the motors in place when we're looking at high power, much heavier motors and higher thrust ejection charges coming out of those motors as well. And so that's a bit more difficult. And so we need a better motor retainer to do that. So there's a number of ways that can be done. That can be done with screws and bolts. And I guess I should say washers to basically screw into the aft centering ring of your rocket and hold the motor in place. There's specifically designed motor retainers that are have basically that are glued in place on the aft motor motor case or tube, excuse me, motor tube, and that cap is screwed on to that, and inside of that is the motor itself, so it's holding it in place that way. Some of the other things that really we need to consider is, again, these rockets are heavier and going faster, so some of the materials for the recovery system, which was mentioned earlier, is where most of the failures occur. Instead of plastic parachutes, we're really looking at parachutes that are made out of ripstop nylon. We're also looking at the shock cords being made out of nylon, Kevlar, or Dyneema instead of elastic. The elastic tends to break, and in fact, it is not permitted to use elastic at the flying field that we're flying at for your shock cords. That's restricted, so it cannot be used. So you really need to look at some other material for your shock cords. Let's move on to the next slide and go there. So some of the construction tools, if you've been building model rockets, you get your kit and you're going to get your balsa wood, and you might have to cut the fins out of balsa wood. And well, how do you do that? You'd use an X-Acto knife basically to cut that out, or to trim some additional pieces of plastic off of your nose cone that you want to trim off because it was molded and has some residue from the mold left there. So you want to trim that off, and then you want to sand it. And so that's how you kind of shape the fins and bevel the fins, is you would sand it or sand these pieces that have been where you've cut off various pieces in order to shape it and get the shape into the smooth and conforming shape with the rest of the component that you're trying to adjust. And then there's other things that you may be doing is in terms of joining the components, using the glues that we've talked previously about. And then also you may want to have some kind of alignment guide where you're lining the fins onto your motor tube. Or your airframe, I should say, where you're actually making sure that they are aligned on the airframe as well as you can get them, so that they're not facing 90 degrees or perpendicularly off the airframe and not angled and so on. Well, high power, it can get much more involved. So there's a lot of different machining tools that can potentially be used based on the material that you are actually using to construct your rocket. Some of the materials we mentioned before, say aluminum, for example, which you could be used for an airframe. Well, we don't have that sophisticated airframes and that are going to be flying at the speeds needed to use that kind of material. So you won't necessarily need to use a milling machine or lathe to shape those or adjust those and or drill through those. But you might want to use some kind of saw, for instance, to if you're going to be using and making your own wood fins, for example, whether it's plywood or maple or some other type of wood, to saw those shapes out. You would probably want to use end up wanting to use some sort of sander, whether it's a belt sander, orbital sander, to shape those fins, or that could also be done with a saw if you're trying to bevel leading edges of fins or trailing edges of fins. Um, Joining pieces together, you may need to drill, tap holes into components, or so that you can screw machine bolts into them. You may have to go and use some other types of glues. We've mentioned adhesives, other adhesives or epoxies earlier, but you could use hot glue for instance, to attach the electronics to various electronics boards within the avionics bay that can be used for those types of purposes, or to hold down wiring in the avionics bay. So there's other types of joining that could be done. And then you'd have a variety of fixtures when you're actually building these particular components and making sure that they remain aligned during the time that the glue is drying. So oftentimes this glue may take, or the epoxies, I should say, may take hours to dry. So you probably do want to have some kind of alignment guide to hold the fins in place, or to make sure that when you're conducting some type of cutting operation, that the cutting operation is being done consistently over the length of the material that you're actually cutting. And if you're cutting a bevel on a fin, for example. All right. So there's quite a few different tools that can be used. Let's move on to the next slide. All right, minimum diameter techniques. We are looking at the minimum diameter rockets are typically the highest thrust rockets and undergo some of the highest accelerations as a consequence of in the high power world of rocketry. And so we're not going to be exceeding 100 Gs as mentioned in the first bullet, but we will be going much faster than a normal high power rocket would go if you're building a minimum diameter. So that means that these rockets, since they are reaching these high velocities, and they also are doing that in generally the lowest part of the atmosphere, you're going to be experiencing a lot of forces on that rocket that are not necessarily typical of the rockets you've flown before. And so this means you're going to have a lot of stress being placed on the fins. And this stress is referred to in a variety of ways, but they're often discussed as flutter, which is the fin moving back and forth, bending back and forth, and divergence, which is actually a waveform kind of going through the fin. This means that those fins really do need to be strong, and they need to be attached very strongly so they do not come off the airframe during the flight. You do not want, and that's referred to as a shred. So you do not want to shred your rocket as it's flying through the air. Uh, so since these components are experiencing such high either tensile, compression, and or shear stresses, the material you select needs to be appropriate for the flight. And the sizing is critical as well, because if you have a very large fin, you're going to go through much greater stresses than you would otherwise. And the joints that are holding them in place are also going to have to withstand all these intense stresses, and those bonds are going to have to hold. So it's important to assess the design that you have and understand the structural safety margins that are needed in order to make sure that the flight is going to occur safely. And so we'll be talking about that in the next slide.
Let me just put one clarification. It turns out for this year's competition, one of the expectations for one of the flights is to go very high, and one way to approach that is to go minimum diameter. That's not a requirement. We just think it would be useful for all teams to understand what they're getting involved in if they elect to try to go minimum diameter.
Yes. All right. Again, as opposed to model rockets, the high power rockets are going to have to withstand typically higher accelerations and loads on those structures. So when you're flying high power rockets, we typically do not recommend the use of cardboard. It certainly can be used in H-class rockets, but again, we have a motor in this competition that is really at the very top of the H-class. So you may want to be looking at other recommendations that we have with respect to the materials that we've mentioned earlier, and that would include fiberglass, carbon fiber, blue tube. Those materials are really designed for higher acceleration flights. And so those, if you choose to use those, you certainly can. And those would be in some ways preferred. The attachment on these types of materials on these airframes also are going to, as I mentioned earlier, experience more significant forces. Where you're going through the atmosphere during these flights, they can certainly be sheared off. And again, in these cases, we would be recommending, tubing, and that could be, again, the fiberglass, carbon fiber, and blue tube. But again, since we're in the lowest level of high power, phenolic tubing or cardboard tubing could be used, but are generally not recommended, for high power flying. However, in this cases, if you want to do that, it could be done. But remember, we're really close to the eye level here with that motor we've selected. So I'd consider using some of these other materials instead. We don't want you to have pieces of that rocket shearing off during the flights. Because then again, those are hard to see, and we just don't want to have, it creates a safety issue if pieces are coming off and coming down if you can't see them. And of course, this also refers to, since these are being attached to the airframe, the material used for joining also needs to be strong enough. And so the white glues and so on that you may have used in model rocketry are just not appropriate. Really need to use epoxies to put these in, hold these in place, or some other kind of fastener, screws and so on. Now, the competition is to go as high as you can with this particular H550 motor. And so you want to minimize the drag and drag forces on the rocket, because if you don't, you're going to go to a lower altitude. So you want to go the highest possible. So you want to eliminate as many of the external protrusions as possible on the rocket. So again, when you're looking at designing the rocket, and if you're looking at putting cameras on it, or other items on it, like rail buttons and so on, you want to try to minimize the surface area that's on the external airframe of the rocket in order to make sure that you can go as high as possible. We'll talk a little bit about that more later in a later slide. Let's move on.
I actually have one comment,
sure, go ahead.
actually, and that is canvas phenolic is, my perception is, it's a souped up phenolic tubing that's even tougher than blue tube. Are you familiar with that product? And if so, would that come in the not recommended or the recommended category?
I think that would be fine, actually. You could certainly use that. We didn't put it on the slide, but I think canvas phenolic should be fine for what we're doing with this competition.
Okay.
All right, motor retention, mentioned that earlier. There are, for minimum diameters, generally the motor retainers that are out there are not designed around minimum diameter rockets. And so for minimum diameter rockets, there's really potentially one or two solutions which we're presenting here. So one is internally holding that motor into the rocket itself. Well, how do you do that? Some of some of the motors, the designs of the cases that the motors have associated with them, there are the cases themselves have forward closures that have a tapped, threaded hole in the top where you can put an eye bolt into those holes. But instead of putting an eye bolt into those tapped holes, you could actually have a threaded rod in those holes that is then attached to a component above that rocket in the airframe that is held in the airframe, so it's actually going to hold the motor in. So when you put the motor in, you would just screw it into that threaded rod. There's a company called Aeropack that makes such devices. That's pictured on the right, and that's that red device that actually has the motor screwed into it. That would be held inside of the airframe, and you see there's also a space for an eye bolt, a forged eye bolt to be screwed into the top. Uh, and so that red component is actually epoxied inside the airframe. Well, that's great if you have a motor that actually needs a case. Well, the motors that are being used in this competition do not require a motor case. They are actually what's referred to as disposable motor systems. So they do not have a case, and they do not have a mechanism to thread into in the upper section of the motor. So that's not going to work very well. You could actually build something that would work for those motors, but the other option that we would consider in this case is external motor retention. And there is not a motor retainer that's truly a minimum diameter, but the one that comes closest is Giant Leap Slimline motor retainer. There's 3 different styles to that. They're very thin. They would be epoxied on the outside of the airframe, and with a higher temperature epoxy that we mentioned JB Weld earlier. And you can see an image of that in the bottom right corner of the slide, where the base is actually just a straight it's a cylindrical piece of aluminum, and it's straight all the way through. Most other motor retainers, they get wider at the very aft end. Well, that's not the case with this one. And so that adds a little bit of width to the airframe where it's attached, but it's very minimal. So that's an option you could certainly consider. You can move on to the next slide then. Okay. So with respect to the building techniques for your fins and essentially the design, you need to design your fins and then make them. So one of the things that you should really, one of the possible options here is to use some simulation tools. OpenRocket is free and available to, oops, oh, there you go. OpenRocket is free and available online, so that's something that you're certainly all welcome to use. RockSim is available from Apogee Rockets, and so that tool I believe is around $130 to purchase, and that's also a very good tool. Both of the tools I've just mentioned really do not handle simulations in the transonic, supersonic ranges very well. And so you're certainly welcome to use the tools. If you're going into those velocities when you're flying with your rocket, you just be aware that the altitudes that are projected may be a little lower than what may actually occur in the flights. And the velocity data will be off as well, and so on. A RAS Arrow is also a free tool online that models rockets in the not only in the subsonic range, but transonic, supersonic, and hypersonic ranges. And so that is a good tool. It is it's a free tool that you can actually use in combination with OpenRocket or RockSim to get some more accurate simulations of the flight data before you build the rocket. during the design process. So, so what you'll want to do is go through the process as you would in your designing your model rocket or high power rocket, but you'll want to really look at iteratively adjusting the fin design to meet the performance requirements. And so one of the things that you need to obviously be looking at in addition to altitude, what you're trying to get to, your maximum altitude, would be the stability margins throughout the entire flight and the velocity. You want that data to look at the next step that you're going to need to follow and that is to try to run the fin design that you come up with through a flutter analysis, a fin analysis. And there are tools that are available either online in GitHub for fin flutter analysis tools. There's one that's been out in called FinSim that can be purchased for a minimum amount of money. I believe $35 is what it used to cost. I think it may no longer be available, but you just have to do a search and check on that. Some people have told me that recently. But what that allows you to do is to provide the parameters of the fin in this particular tool and the size of the airframe that you're putting on it. And that you can provide the fin thickness, the shape of the fin, the material that's being used, the size of the fin fillets and the epoxy that's being used. And then you can model that fin during the flight, putting in the maximum velocity you're going to hit and at the altitude you're going to hit it. And then you can model that and determine, well, is my fin going to hold up? Is it going to, based on the material it's made out of, is that fin going to break, either through fin flutter or fin divergence? And so you might want to, actually, you probably want to try a number of different speeds and altitude, and that's why you want to run the simulations in OpenRocket or whichever tool you choose and see how fast you're going at different altitudes. And so you make a good determination of, well, all right, maybe it's probably going to be where you're going to hit the fastest because you're probably going to go fastest at a very low point in the atmosphere. And so you're going to have the greatest forces on that particular fin, most likely at that point. But you probably want to just try one or two other points and just see what it actually comes up with. If you're using some publicly available or individually developed fin flutter analysis tools, which are you can find them in GitHub or other spreadsheets that may be out in the internet portion of the world, you can certainly use those. But they haven't necessarily been through as much of the use and analysis as some of these other like FinSim tools have been through. And so you might want to have a larger safety of margin because you're trying to optimize these. And NASA, when they make their fins and for their rockets, they obviously have very sophisticated analysis programs, and they generally recommend that they have a 15% margin of between the fastest speed and the speed they're going to fly in order to make sure that they do not have an issue with their fins. But I would recommend, in this case, so you look at least a 25% safety margin, so make sure that your fins do not break through the flight. All right,
So I just want to remind people actually that for this competition, you are expected to design before you build, and you're expected to show people your design. And
right.
those people would include your certified mentor, as well as Gary, who is the technical advisor. And so you are expected to try to do this, but you will also get help, and that's completely fine. Gary, in particular, is well aware of these things and can serve as a resource for you.
Yeah. Yes, happy to do that. And so please feel free to reach out to your mentor and to me in order to help you with any of these particular items. All right, so So these fin simulation programs will typically want to know specific information. They're going to want to know, well, what's the radius of my fin fillet? What's the length of the fin fillet? Usually it's the length of the root cord of the fin, which is on the airframe. They're going to want to know, well, what type of joint are you using? A butt joint means the fin is just attached to the airframe, basically on the outside of the airframe or through the wall. That phrase is referring to fins that actually go through the wall of the airframe into the rocket itself. Uh, well, if you're building a minimum diameter rocket, you can't go through the wall, because when you go through the wall, since the fin is on the aft end of the rocket and so is the motor, you're going right into the motor. So you're really not going to have through the wall. So you're going to have that fin. It's going to be what's called a butt joint, and it's going to be that fin's going to be held to the airframe with the adhesive, whatever adhesive you've used. So the adhesive is very important in terms of what's being used and how you actually apply that adhesive. And so you will probably end up wanting to rough up the airframe where those fins are going to be, so they have a good attachment point. The adhesive has a good attachment point to the airframe, as well as the root cord of the fin, and so on. So there's a variety of construction techniques associated with that, but the adhesive needs to be very strong. So so you need to know the adhesive strength, because that's going to be required in the modeling of the fin attachment when we look at whether it's going to fail or not during the flight. You're going to want to make sure, as I mentioned earlier, the velocities at specific altitudes, so we can model it's a couple of different points and make sure that we're looking at the right area of the flight in order to make sure what the maximum forces are on that particular fin. Angle of attack is important. So we're going to be launching our rockets vertically. All right. So just that's how we're going to launch them. And so our angle of attack of the rocket into the flight path should be 0, because we're flying right directly vertically. But throughout the flight, rockets tend to oscillate, especially if your stability margin isn't where it should be, but they'll tend to oscillate a little bit. So you'll probably want to actually, some of these tools like FinSim, for example, you can look at how that adhesive is performing under different angles of attack with respect to the fin. And so we're probably looking at just a couple of degrees at most, but if you get further off, that there is certainly a much greater stress on the fin. You'll also need to know some other information, where the center of gravity of the fin is, something called the elastic axis, which I can help you with, but basically it's a line along the fin where if you apply force, the fin only bends. It doesn't create any torsional or angling forces on the fin at all. So that's what an elastic axis is, if you see the term when you're looking at these different potential applications. So you'll also need to look at the material you're using for the fin. Sometimes the material is not homogeneous. I mean, if you have plywood, right? You have different. It's probably the same wood, but it's at a different angles. Within the plywood that's put in. It's when the plywood's been made. If you look at if you look at carbon fiber or fiberglass, it's also it's not a homogeneous material like a metal. Aluminum, for instance, or some metal that's homogeneous. But fiberglass and carbon fiber, we all know those are made out of strands of those materials, but they have epoxies in them. And so these tools often are assuming, one of their assumptions is that the material you have is homogeneous. But you can get information about the material and then still put that into the tools so that you can model them, even though they may be heterogeneous materials. So um, so you'll need to know the modulus of elasticity. You can look these up, the density, Poisson's ratio, and so on. There's a list here that you generally will need in order to use these tools. Uh, And so you can either find that for the material you're using, or if you're using something that you're coming up with yourself in terms of designing and making your own fins that have multiple different materials in them, you would have to actually conduct some tests on those materials in order to make sure that you have the right information so that we can model them properly. And then finally, I think in particular, since we're using butt joints, I would highly recommend that if you're actually making a minimum diameter rocket, that you actually use tip-to-tip layups for your fins, and that by doing that, it's going to, and I'll talk about that in just a minute, what that is, but in doing that, you're actually going to add additional layers to support and strengthen the fins and the joints holding it to the airframe. And as such, you're really creating, again, a material that's not, it's heterogeneous, not homogeneous. So we'd have to make and adjust some of these pieces of information in order to model that correctly for these fin simulations programs. So, so as long as we're talking about these layups, here's a couple of different methods that you can actually lay up fins on minimum diameter rockets where you have butt joints. The first one is pinning the fins into the fillets, basically. And what that means is that we need to make an adjustment to the fins. And one way of doing that is along the root cord is to drill holes in the fin itself along the root cord. And these holes need to be small enough and low enough on the fin so that the fin fillet, when you put the fin fillet onto the airframe and the fin and hold the fin in place, that these holes are going to be completely covered. And so what happens is that,
So Gary,
yeah,
can I ask for a clarification? When you talk about drilling holes, I haven't
yeah,
done this myself.
yeah,
Are you drilling holes sideways through the fin from one
yeah.
surface to the opposite surface, or are you drilling up into the root, up
Ah,
into the fin?
thank you. I will make the clarification. Yes, it's from one side of the fin to the other. So it's not it's across the width of the fin material. So
Okay.
if you have a 1/4 inch material, fin material, it's from one side of that 1/4 inch material to the other along the root cord.
And then underneath what is going to be covered with a fin fillet.
That's correct.
Okay.
Yes. So yeah, so when you put that fin, when you put the fin on the airframe and then you put it in a fixture, hold it in place, however you're going to do that. I mean, you may hold it in place by just putting super glue, yeah, on some of the bottom edge of the fin. But however you hold it in place, you can then, when you apply the epoxy to create the fillet, that epoxy will go through all of those holes that you have along the root cord to the opposite side. And you'll fill in, obviously, fillets on both sides. And then when that epoxy um, dries, basically, or cures, what you'll end up having then is that not only the fin fillet holding along the sides of the fin, and of course along the airframe, but also it will have the epoxy going through, which will create more surface area for the epoxy to hold the fin in place. And the epoxy itself is holding the fin down and in place onto the airframe. Now, so that's the idea there. There's depending on the epoxies you use and so on, there's some other additions that you could use. You could put in those holes or along that holes or in the epoxy itself. You can put chopped fiberglass or carbon fiber or other materials to help strengthen the epoxy and also strengthen the the epoxy through those holes as well to hold it in place. So there's a lot of different modifications that you can consider there. Um, so again, I mentioned the pro here. The pros for this particular technique is that it does increase the surface area that the epoxy is holding onto the fin with. The con is that it's weakening the structural integrity of the fin. So those holes, when you're drilling them through, it's really weakening the fin a little bit. But that method has been used in a variety of ways, and it is and has been successful. Another way that's used more often these days is what's called a tip-to-tip layup. And this is taking your fin, basically attaching it to the airframe, generally with a fin fillet underneath, or basically along the sides of the fin as you normally would. And then once that epoxy is cured and the fin fillet's fully formed the way you'd like it, between two fins on your airframe, if you have a 4-fin airframe, let's just say each fin is 90 degrees apart, you would take and you would cut out a piece of, let's just say you're going to use fiberglass, and you would lay that on the surface of the airframe and epoxy it to the surface of the airframe and up 1/3 of the distance from the root cord to the tip of the fin. So about 1/3 of the way up. And you'd epoxy that in place along the fin and the airframe on both sides. And then you would do that again with another layer of fiberglass. And this time, though, you would go 2/3 of the way up of the fin. And then you would do this with a third layer of fiberglass as well, epoxy it in place, and go all the way, you pass through to the tip of the fin. And then, of course, when it's all cured, the epoxy is cured, you cut off all the excess fiberglass. In this case, that's along the tip of the fin, along the leading edge of the fin, and along the trailing edge of the fin. So you cut that off and smooth that off. So it's epoxied all the way across the leading edge and trailing edges as well. This way, what you've done is now you've created 3 layers of fiberglass that are actually holding the fin to the airframe. And the fins, I should say, to the airframe, and also supporting the structure of the fin at the very base, and that structure is just getting slightly narrow as you're going to the top. And where the fins normally break is when they have a fin flutter issue or fin divergence issue is right near the root cord. So you're strengthening it up there. And so these larger surface areas really provide a strong holding mechanism to make that attachment be secure. The con, of course, is you are thickening the airframe up and around the circumference of the airframe, and you are thickening the fins, and so you are increasing the drag. So, and increasing the drag, if you're trying to go as high as possible, is not ideal. But losing your fins on the way up isn't ideal either. So anyway, these are 2 techniques you can consider using. All right, let's move on to the next one. So let's talk about nose cones a little bit. So nose cones have a variety of designs, and they are very different in terms of their performance in various realms of speed that you can go. So generally, the best shaped nose cones work in a certain realm, velocity realm. And so for subsonic flights, elliptical nose cones are generally the best performing. In transonic flights, you have the LD hack, you have half power series nose cones, which, by the way, unless you make it yourself, you really don't find those commercially available. Generally, what you will find is the LV hack nose cones that are available, and that's really for typically less than Mach 1. When you go supersonics, you generally the best nose cones is an Eggers minimum design shape, but the X to the 3/4 power series is what you kind of see most if if people are actually making their own. Again, because neither of those nose cones are available, typically people are still using the LV hack nose cones in the low supersonic ranges. And then we're not going hypersonic, but there's a couple of different nose cones that are available there. So if we go to the next slide, we can actually see a chart.
I've got a question for you,
Oh,
actually, and
sure.
that is, I see that ogive is not on your list at all, so it's
Hmm.
not best for performance in any way, but why is that the most common nose cone that you can buy?
It's easy to make.
It's easy to fabricate. Okay, fair enough.
Yeah, but it's here in this particular chart. It's the first one up there, tangent ogive, and one's best, four is least best, and you'll see that um, as you'll see in the chart, tangent ogive and conical are basically four across the board. Uh, they're not, and by the way, the x-axis of the chart is showing Mach numbers. So this only goes to between the transonic region, which starts at 0.8 Mach, and then goes up to just a little over Mach 2. And so you'll see LV hack is the third one in the list. Well, it starts out below Mach 1 as 1, and then as it breaks into Mach, it goes to a 3, so it's not great. Um, and so you can just look at this chart and see what the different values are. Um, one of the things that generally speaking, and when you look at it, particularly at LV hack nose cones, is that the optimal fineness ratio is 5. Well, what the heck is that, right? So the fineness ratio is the ratio of the length to the diameter. So if the nose cone is 1 inch in diameter, then it should be 5 inches long. And this does not include the shoulder of the nose cone, right? It's just the exposed section of the nose cone. And then that will give you the best performance. If it's only 3 inches long in that particular example, the performance will be deteriorated. Um, and so generally what you'll find is most of these nose cones that are made and available today for the have a fineness ratio of 5, and because that's the optimal one. You get a slight improvements a little bit longer, but it's not really worth it. You're adding more weight, and the improvement is so minimal that it's just doesn't make sense. Um, The bluntness ratio is the curvature at the very tip of the nose. Typically, they're not pointed; they're actually curved slightly, and the 0.15 is a reference to the actual diameter of the nose cone, base of the nose cone. So that's the reference to the base. So, um, okay, so let's move on. So we need to go to maximum altitude. We need to think about drag. And so there are some major components of drag that we need to think about. So skin friction drag is one of them. So the surface of the airframe, the nose, the fins, and so on. So they all have exposed components out into the atmosphere during the flight. And so you want to make those as smooth and as polished as possible, those surfaces, and in order to minimize your surface drag. Now, keep in mind to do that, that means you're going to be adding paint and smoothing that off, sanding that down, smoothing it off, and so on. Well, paint, you're adding weight. So it's a trade-off. You have a trade-off between the weight that you're adding and the hopefully the reduction of drag that you're creating. And so you need to keep in mind that these tools that we're using, like OpenRocket and RockSim, they have different drag levels, and so for your skin friction. So I'll just use RockSim as an example. They'll have polished, gloss, uh, um, and then there's there's a medium one and a rough one. They have four options. Uh, Gloss would be like a car finish. All right. So typically you're not selecting that level when you're actually trying to model your flight, unless you really have an auto body to finish or capability of creating that kind of finish on your rocket. So keep in mind the manuals for these particular tools explain the surface finish and what kind of roughness they have in terms of thousandths of an inch. So all right. So protrusions. So this includes a number of different items that are protruding out of the outside the airframe. Well, okay, your fins are protruding, obviously, but you also have rail buttons and so on. So there's you'd potentially have camera shrouds if you're putting a camera outside the airframe. So those are things that you need to consider. So for rail buttons, well, you could use flyaway rail buttons. These are rail buttons that are actually held to the outside of the rocket with a device that goes around the airframe and rubber bands that once the rail buttons actually leave the rail, the rubber bands snap it open and it falls off the rocket. And people have used those to some success, not with really large high power rockets, but certainly, smaller ones. The only thing is occasionally when they come off, they may damage a fin. So you just need to be aware of that and make sure that your fin is made out of a material that wouldn't necessarily get damaged if if it actually hit the fin on the way off. So just keep that in mind. Another option is, well, we won't use rail buttons. Well, then what are we going to do? Well, there's a type of launcher called a tower launcher, which has basically rails that are between the fins and allows the rocket to slide up by keeping those rails holding the airframe of the rocket in place until it leaves the tower. And so at TripoliMN, Minnesota, where we're having the competition, we have one of those available. And it has a rail that's the rails are 6 feet long. So that's the maximum length of that particular tower launcher. And so that could potentially be used. And keep in mind that there is some additional drag being exerted on the rocket because of those rails for that 6 feet while it's in that tower launcher before it leaves, rather than just the rail buttons going through a rail as they normally would. So it's probably not all that significant, but just keep in mind that it does exist. And then there's something called interference drag, which is produced not only at the protrusions, but the interface between the protrusions and the airframe. And those kinds of, and that's essentially if you think of your fins and you think of the epoxy that you're creating the fin fillet with, that fin fillet is producing this drag. And so you can minimize that by properly sizing and smoothing out those areas and making sure that they are shaped in very well and very smoothly. So you can minimize drag there. And I will just give you a tip that the optimum radius for these fin fillets between around the fin fillets is basically between 4 and 8% of the length of the ripcord. That should be the radius between 4 and 8%. That's again, that's work that NASA has done in the past, and it's just and that's how I make all my fin fillets. Okay, rotational drag. That's to avoid any sort of angling or canting of the fin as when it's attached to the airframe. So because if it's angled slightly or canted slightly on the airframe, you can actually create more rotation of the rocket through the air. That rotation creates more drag as the rocket is flying because of the fins, of course. And so you want to minimize that. So you want to try to attach those fins perfectly to the airframe. And then there's base drag. And base drag is really on the aft end of the rocket, on the airframe. There is a space there that once the motor burns out, that basically isn't being filled with air. There's air going past it, and the air is trying to fill that empty space because that's as moving forward, you're creating space, is trying to fill it. So there's basically turbulence trying to fill that space. Well, you can minimize that space by putting a boat tail on the aft end of your rocket. So making that space smaller and narrower by having a boat tail in place. Or you can somehow expel gas out of the aft end of the rocket and fill that space with gas, and then that turbulence won't be created. That's why it doesn't really exist why the motor's firing, because the motor's putting gas out of the back end and pushing the rocket forward. So that's another type of drag that you could consider and try to minimize. All right, let's move on to the next one.
Let me just make a quick comment. So
Sure.
basically, when you're trying to fly high, drag considerations are important. You may or may not try minimum diameter, but it turns out that my understanding, correct me if this is not correct, Gary, is that a boat tail brings a larger rocket down to minimum diameter. In other words, it brings it
Yeah.
down to the size of the motor. If you already have a minimum diameter rocket, you can't really add a boat tail to that. Is that true?
Yeah, that is correct. That is correct. Yeah,
Okay.
yeah, that's a good point. I didn't mention that, but yes, you've already got the minimum size. The only thing it potentially could do, yeah, you really can't. You really can't. Not in any sort of a way that would really make sense. So yeah, because you could try just to get to the nozzle of the motor, which is going to be less than the diameter of the motor, but yeah, that creates other potential issues, and you'd have to do it potentially in such a short space because the boat tail would have to contain the diameter of the motor that it's really would be not worth it. You'd still have the turbulence there and the low pressure area.
Okay, so a few final slides about safety. But one more thing, and that is for this particular competition, you're expected to fly twice, once to a specific altitude that's not that high, and then once as high as possible. So most of our discussion in this video has been about going as high as possible, but that's only half of what you are expected to do. But hopefully many of these ideas can serve your general understanding of high power rocketry for both designs. A few things about safety. First, some just general construction safety. So if you're using machine equipment, you have to make sure that you don't get caught in the equipment. And so watch your hair, watch your jewelry, watch your loose clothing, wear eye protection, please, always. And then make sure that your hands and other things don't get pulled into any cutting operations, perhaps by using appropriate tools for pushing your materials through the cutting operations rather than your hands. And always make sure you know what you need to do with every machine. And typically there would be a shop personnel to ask and perhaps the shop personnel to oversee or even to assist while you're doing machining.
Yeah, let me just add something to that
Sure.
quickly, is that if you're going to be using equipment, and you're in particular, if you're not familiar with it, you really should have a second person there. And I don't want to be morbid, but I do want to make sure that everybody understands the equipment can be very dangerous. I mean, there's in the sense that there are certainly incidents that have occurred where somebody has gone into a school machine shop, for example, to work at on machine late at night, and they got their hair caught in the lathe and it choked them to death, right? Or so it can have very serious consequences. And so really try to do this in pairs, at least, and certainly have people there to watch what you're doing. So
Yes, very good advice.
yeah.
Some more comments about the materials. So it turns out that basically some of the materials you're using, especially things like fiberglass, if you're cutting it, it can scratch you, it can produce dust, which can get in your eyes, get in your lungs. If you're using oil for certain kinds of machining tasks, that also can potentially get hot and burn you or get on your skin, or eyes or lungs. So there will be safety considerations, and often that will involve, always that will involve eye protection. Often that will involve protecting other parts of your body and possibly wearing masks and stuff to make sure that you don't inhale things. Some of the epoxies that you'll use and some of the propellants associated with the motors are actually toxic. So make sure you're familiar with the material safety data sheets for the materials that you're using and follow the procedures, including ventilation, including protective gloves and other things. And make sure that if you happen to touch these things that you're not supposed to touch or be exposed to them, that you follow the material safety data sheet as far as how to deal with that, including washing up, including seeking medical attention if that's appropriate. Generally speaking, always wash your hands after you do any of these tasks, even if you're not working with something that you believe is toxic, and always, for sure, if you know that it is toxic. This also applies to soldering. If you're soldering with solder that contains lead, don't breathe in the smoke that comes off of the rosins, and wash your hands after you're done. And then, of course, for soldering, don't burn yourself and certainly don't burn anybody else. Gary, why don't you take the last few slides?
Oh, all right. Okay, so the other thing you're going to be dealing with are basically low explosives, and so one of these areas that you're going to deal with that in has to do with the ejection charges for deploying the parachutes, and also is going to be dealing with the motors and the igniters associated with those. So, with respect to the ejection charges. Again, the same safety, similar safety requirements really you should employ are wearing a face shield or goggles. You want to make sure that if the charge for whatever reason goes off, that your face is protected. You want to make sure that doesn't happen. So you want to do things like short out E-matches by twisting the wires, the open wires together, and making sure that they can't have a current going through them. You want to can basically make sure that the black powder is also when you actually build your charges and you put them in the rocket, that they're going to work. Right. So in order to make them work, in order for them to fire, those E-matches have to essentially be in contact with that black powder. So if you're using a canister or some other mechanism, you just need to make sure that, oh, I'm not filling the canister the whole way. So I need to put some cellulose or something else on top of the black powder with the E-matches in the bottom of that canister, and make sure that it holds that black powder in place, and then tape over the top of the canister. Or if using a surgical tube, something similar to that. You actually fill that space with again, cellulose or some other mechanism, and then glue the ends of the tube together. So, and then you definitely, again, this needs to be in your checklist, by the way. You do not turn on once you're going to connect everything together, you make sure the avionics is off and it stays off until the rocket is on the pad and vertical. You do not turn on any of your avionics that is going to be connected to any charges. Again, we don't want charges going off in the camp when your rail is horizontal and you've got people standing by it. You don't want charges going off and ejecting portions of the rocket into someone, that kind of thing. So, okay.
So one quick comment, and that is, at our competition, we will help. In fact,
Yeah.
upon request, we will produce ejection charges for you, but this isn't good enough. And the reason this isn't good enough is you're expected before the competition to do one or more test flights. So you need to be aware of and either be prepared to produce ejection charges or work with someone who's able to do that. For instance, your mentor.
Yes. Now, igniter, similarly, we don't want the igniters in the motor, and it's actually Triple E, NAR, National Association of Rocketry rules in the motor until the rocket is actually vertical on the pad. The reason for that, of course, is if for some reason somehow that igniter fired and started the motor, we want the rocket to go up and away from everyone. We don't want it to be going horizontally across the field and flying, towards somebody or some property, a vehicle or whatever, and either hurting an individual, which is the most important thing. We don't want that to happen. Less important, but still important is damaging something else. But with respect to igniters, that's the last thing you do. You put the rocket on the rail, you stand it up, you do whatever you're going to do in terms of photos and so on. You arm the electronics, then you put the igniter in. Well, why are we arming the electronics? We're arming the electronics first because, again, if somehow that the igniter is for some reason goes off, there's some kind of failure that makes that happen. We want to make sure that when the rocket finishes its flight and reaches apogee, that the parachutes are coming out. If those electronics are not on, that rocket's going to come back down ballistic. And again, it's coming in ballistic. It's heavier, it's fast, and it's going to potentially hurt an individual if it hits them, or damage again a vehicle or property or something else if it hits that. So we want to avoid that. So that this is a safety concern. So you want to make sure that that is also in your checklist. All right. So in order for that igniter to work, especially in certain brand motors like Cicerone motors, that igniter has to be all the way to the top of the motor. And even in all motors, you want it all the way to the top so that when the igniter starts the motor, that flame front from the motor is going down the entire length of the motor and going out the nozzle. You don't want the igniter in the middle. So you have a flame front going up and a flame front going down, and then they're reflecting back and forth and potentially creating pressure waves in the motor. So you want it all the way at the top, and it needs to stay there. It doesn't. You want it to stay there. And remember, the igniter it's gonna be connected to the firing system, which means alligator clips connected to the igniter wire, and that igniter wire is actually going to if it's windy, the rocket's going to be moving on the pad, and you don't want that igniter pulled out or pulled down. So you need to secure it in the motor so it doesn't move. And then when you actually are finished with that, you've got to make sure that the igniter wire and the alligator clips that they're connected to are not touching they're not touching each other or any other piece of metal on the blast plate or anything else. They need to be basically in an area that has enough resistance that they can't create a short. Because if there's a short, then when we try to fire it, it's not going to work. If both the alligator clips are sitting on the blast plate, that could happen. In fact, it just happened the last launch I was at. So you really need to make sure that they are basically hanging in the air separate from one another or on the ground or somehow separated from one another so that doesn't happen. And then there's a continuity test. We'll have pad managers there to help you do the continuity test. But basically, what you'll find at our launch site, there's a button that's leading to the wires that are going to your pad. You can press it. If it's green, you have continuity. If it's red, you don't. And if it's red, then you need to recheck your igniter and all the wiring associated because something's not correct. All right.
On the other hand, if it's green, that could mean it's shorted. So green,
That's true.
green doesn't mean perfect, but red means definitely something is wrong.
Right. Absolutely. All right. Okay. So I've been mentioning this a few times, but you really do want to create a checklist for every aspect of your rocket preparation. So you probably will have one or two people that are going to be assembling the motor, and you're going to have a few people or a couple of people dealing with assembling the avionics and the recovery system and so on. So these you'll probably have different sections in your checklist to cover these specific items. But if there are dependencies between these items in your checklist, make sure you notify or have that in the checklist so people know, well, I can't do these steps until this is done. And so you need to check with that person in order to continue on. But so you need to obviously go through and assemble, in there. You really make sure that these steps are covering not only all the assembly processes for the motor, recovery system, avionics, payloads, etc., but they also need to make sure and should make sure that you have in the list all the tools you need to conduct those steps. I can tell you that the teams regularly don't have the tools they need to actually conduct the steps that they need to conduct in order to assemble the rocket. They've forgotten them or left them at home. So there needs to be there needs to be the list of tools in the checklist that are needed. So whoever is going to do it or can get those tools ready and then start working on that particular portion of the rocket. And you should really have a packing checklist to make sure that all those tools are packed before you come out. Okay, and then finally, somebody should be monitoring what each person is doing and making sure they're checking off items on the checklist to make sure that all the steps are done and that they've been done properly. And so that you have a second person observing that and making sure nothing gets missed.
So
Okay,
that last point about including checking for live charges, it's very important when the
yeah.
rocket is recovered that you understand whether or not there still is anything explosive in the rocket. And if there is, you need to have a well-documented procedure to deal with that.
Yes, we don't want someone getting hurt when they're actually out there and going through and trying to recover the rocket. So that needs to be checked. Okay. All right, so you've made the checklist, or you've put that all together, and so when you've done that, uh, you're not done. Okay, you're really not done. So you really, somebody's putting this together, different people are putting different sections of together, and you really need to know that that check is comprehensive. You need to know that all the sequences in the checklist are in the correct order. All the steps are in the correct order. You have all the pieces and tools that you need, the components and tools and so on. So you need to go through this and um, make sure that it's going to work, because right now you actually don't know that this checklist is workable because you actually haven't tested it. So you need to test it, right? Just like you go out and test your ejection charges to make sure that they're going to eject your parachutes, or just as we have you do a flight test before you come to the competition to make sure that your rocket's going to fly successfully, you need to check your checklists. And those are good times actually to test them. I would recommend testing your checklist before you do your flight test, by the way. But so somebody should be noting when you're doing these tests, all right, where do the checklists where are they not where are they missing things? Where are they not in the correct sequences? What do we need to do to fix it? And so on, because you don't really know that they're working yet. So you really need to practice going through your checklists as you would in the field and assembling your entire subsystem and rocket. And by the way, that is excluding the charge, at least using black powder. You can use a substitute substance, but not black powder, right? And it also excludes the motor. You can use a substitute pretend motor, but not the actual motor. We don't want you doing that in your classrooms or wherever. Or in a house or whatever the case may be. So you could just use a piece of wire to pretend it's an igniter that's just bent over. It has no pyrogen on it, whatever, to pretend simulate what we're doing. So again, if you do that, you can time it. You're going to have an hour to prepare your rocket, or two, a couple hours to prepare your rocket. So you put this together. Oftentimes, teams haven't practiced their checklists and or assembling their components. So they get there and it takes them 3 or 4 hours to get their rocket ready. And you're basically losing points. So if you actually practice doing it a few times, get it down in terms of how everything has to flow, you're going to be way ahead and be able to assemble everything in a reasonable amount of time and get your rockets ready. Okay. Okay. Now, the last thing really is that we're following Tripoli rules. This is a Tripoli club. We're following the rules for this competition as from an operational perspective in the flights. We have a number of rules that have been created over the last 40 years that Tripoli's existed, or so, 50 years. And they're basically for your safety and the safety of others. So please follow all the Tripoli rules. If you're not, we'll let you know. But really, try to follow all the safety rules. So if the prefect is telling you the range is closed, you can't go beyond the flight line towards the pads. If it's open, you can. And so on. We'll be going through those the day of the major ones the day of the launch, but you can certainly look at those rules. For example, we don't want any open flames within 25 feet of anyone's motor, right? So uh, uh, that includes smoking, vaping, whatever may be going on. But we just don't want that those kinds of risks being safety violations, because you could accidentally start a motor, and that would not be good. Okay. All the mentors, volunteers, and people that have volunteered to participate in the launch personnel, they're there to assist you. They volunteered to be there. They want to see you fly. They want to help you out. So you're going to have pad managers. You're going to have range safety individuals that are going to be reviewing your rockets before they fly. You're going to have a launch control officer directing you what pad to put your rocket on, and so on. All these individuals are experienced flyers. They're level 2, level 3 flyers for the most part, and will be able to help you out and answer your questions. Certainly go to your mentors, and if they're there, and they may not be, you can certainly come to me. I'm the technical advisor for the competition, and I'll help you out. But there'll be other people there that can help you out as well. And don't hesitate to ask any questions. We're all excited to have you at the launch and in the competition, and want to make sure that you're as successful as possible. And so everybody's going to be willing to answer any questions you have and help you as much as they can. All right. Well, thank you.
Yeah, I just wanted to remind you, everybody who's doing any certification attempts, okay, needs to, of course, let us know in advance, and also needs to sign up to become a club member, okay? And so I say that's natural, but it turns out that one of the rules will be only club members are allowed to help set up the rocket. So our expectation is that every team, even teams that are not doing any certification attempts, will sign up a few people to be club members, and those people will be the ones who will be allowed to go out to the pads and set up the rocket. And if you haven't set up a rocket on one of our pads before, that's fine. We will assist with that.
Yeah. And you mean Tripoli members, right?
Yes.
Yeah. Okay. All right. Yeah.
So anyway, thank you everybody for your attention. Thank you, Gary, for putting together those slides and talking through them, and looking forward to the competition.
So am I. All right. Good luck, everyone.
Good luck.